In this video, we discuss stability issues related to Gaussian and Gauss-Jordan elimination. These elimination algorithms are, in practice, always performed on a computer. The interesting real-world applications are simply too large to deal with by hand. Once you start working on a computer, errors start to accumulate. There are different types of errors that we could consider, but the easiest to conceptualize is rounding error. For example, suppose your matrix contains the fraction 1/3. When this matrix is entered into MATLAB or whatever you're using, the 1/3 is not stored as a fraction, but as a decimal. Probably this decimal. One would hope that this level of rounding error doesn't hurt anything, but it is there. Now, suppose you're performing row reduction on this matrix. Gaussian elimination propagates error. The next step will be to multiply the first row to -2 and add it to the second row, and the matrix you get should be as follows. But in fact, it's stored in our computer software as these decimals. So you see, the error has spread. Previously, all but one of the matrix entries was being stored accurately. Now two of the matrix entries have rounding error in them. So Gaussian elimination has made the situation worse. Admittedly, not much worse. But suppose you're performing row reduction on a large matrix. Say A is 10,000 by 10,001. If you had an equation with 10,000 variables and 10,000 unknowns, in real-life applications, systems of this size are common, and maybe every entry of the matrix is a fraction like this. Gaussian elimination in this case will take about 2/3 of 10,000 cubed flops, or about 666 billion, 666 operations. Now, any individual operation shouldn't cause much trouble. Going from exactly 1/3 to this was a very small amount of rounding error. But if every one of these 666 billion, 666,666 steps causes a small rounding error, well, if you take this many small rounding errors and add them together, you might wind up with very significant error at the end of the process. And Gaussian elimination, as we have presented it, is prey to this sort of issue. Computer algorithms use a technique called partial pivoting to combat this. Partial pivoting is using row swaps to always use the largest number possible when doing the elimination steps of Gaussian elimination. So say we have this matrix and we want to do Gaussian elimination on it. We'd swap rows so that this 12, the largest number in this column, is in the upper left. And then we'd be using the largest number possible to eliminate the smaller numbers. The question of why this partial pivoting step works is outside the scope of this course. Even with partial pivoting, Gaussian elimination is technically a bad algorithm in the sense that it is possible to create pathological matrices where the process doesn't work well numerically. However, in practice, this isn't an issue. When Gaussian elimination fails due to numerical issues, it's because the matrix was grown in a lab to make it fail. That's what I mean by pathological. In this video, we discussed stability and partial pivoting. We've made the observation that in practice, Gaussian and Gauss-Jordan elimination are numerically reliable processes, even if it's possible to create bad matrices where they give inaccurate results due to numerical issues. Those bad matrices don't show up in practice.